Scientists recently opened up an AI model's internal processing and found something they didn't program. The model had grown the exact same navigation cells that a biological mouse uses to find its way around a physical room. To solve formatting tasks like figuring out if a sentence will fit on a line, the AI wasn't directly counting characters. It was estimating word pieces and multiplying them, inventing its own internal tools to solve problems it was never explicitly taught how to handle. Because these digital neural structures emerge spontaneously during training, researchers are having to adopt an entirely new framework to study them. They're calling it robo-psychology. We can no longer treat these models as simple calculators. When a system spontaneously grows biological mimicry to navigate text, we have to manage it as an unpredictable alien intelligence. To get reliable, enterprise-grade work from this unpredictable intelligence, engineers must build a cage around it. They construct Mattis's adversarial multi-agent architectures. Take the popular JavaScript toolkit Bun. They just pulled off an enormous code rewrite, moving from Zig to Rust in 11 days, by deploying a fleet of up to 64 AI agents working in parallel. Every single agent writing code was paired with 2 reviewer agents, whose job was to prove it wrong. This setup pushed production to ridiculous speeds, peaking near 1,300 lines of code per minute and generating thousands of automated commits. But the speed triggered an immediate backlash. The creator of Zig, the language Bon abandoned, publicly condemned the result, calling the AI output unreviewed, low-quality slop and trading personal jabs. Deploying fleets of autonomous agents accelerates development to a pace humans cannot match, but it also introduces bitter friction into the developer community, forcing us to completely rethink how we vet and trust code. Giving agents autonomy to execute commands and browse the web creates terrifying security blind spots. Traditional digital firewalls simply don't know how to catch them. We saw this when developers discovered xAI's open-source coding assistant had been quietly uploading entire folders of sensitive user files, including SSH keys and password databases, straight to xAI servers without explicit permission. Security researchers call this the lethal trifecta. It happens when an assistant holds your private data, has active internet access, and encounters content written by an attacker. Anthropic's Claude fell into exactly this trap. A fake web page with hidden links tricked the tool into systematically leaking a user's name, location, and employer. Anthropic issued a hard patch, completely stripping the tool's ability to follow secondary links. An AI's core directive to be helpful creates a fundamental security hole. In these systems, an attacker doesn't need to find a technical bug. They only need a prompt that tricks the agent into surrendering your secrets. We have reached the breaking point of human oversight. When human experts try to catch prompt injections, hidden instructions meant to hijack an AI's behavior, they only succeed about 13% of the time. The failure rate is so high that OpenAI built an entirely new model, trained with massive computing power, called GPT-RED. Its only dedicated job is to hunt and hack other AI models before they ship. This chart compares the tiny 13% success rate of human red teamers against the massive 84% success rate of GPT-RED at breaching security protocols. The AI ecosystem has simply grown too complex for humans to secure manually. We are locked into an automated arms race where the only effective way to police a machine is with another machine. The advertised price of a base model tells you almost nothing about what it actually costs to run. The enterprise reality is that the true financial burden lies in the escalating computational cost of the surrounding infrastructure. If you try to control the model by adding massive instruction harnesses, like strapping on 5,000 words of rigid rules, you can actively degrade its performance. In recent tests, overloading a smarter model with stale instructions caused it to fail its task entirely. Instead, the costs pile up in hidden engineering choices. Caching behaviors and complex multi-agent routing loops drastically multiply your final token usage, often making a model with a cheaper per-word list price more expensive in practice. AI intelligence is now a commodity. The defining engineering challenge has moved to the infrastructure, the context management, the cost controls, and the security plumbing required to make the model actually work.